Okay, so basically we're going to start with the definition. There's probably some stuff missed. But, so what are lipids? So lipids, there are two major categories of lipids. It's either So what are the main components of lipids, right? So it's either the molecules that will contain fatty acids or steroids. So you can see steroid nucleus on the right. All lipids are hydrophobic, which means they are not soluble in water. They are soluble in various organic solvents though. Okay? The name is derived from the Greek word for fat, and they play absolutely crucial roles in the cellular membranes in the form of phospholipids. They comprise a lot of fat-soluble vitamins, participate in the energy storage, and also form a variety of various steroid hormones, from mineralocorticoids to glucocorticoids to androgens. So lipids can be generally divided into two large categories. First of them are esters. Remember, we basically just finished talking about them. A typical ester is formed by the carboxylic acid and alcohol. Okay? Now the second, and that category, the category of esters, will include a wide variety of lipids, from waxes and fats to oils and phospholipids. A completely different type of lipids are steroids. So these guys do not contain fatty acids. They are rather just hydrocarbon rings fused together, and that means that they cannot be hydrolyzed. So if you look at a carboxylic acid plus alcohol formation, if you look at the ester, we were talking about this, you can break down an ester either by acid, converting the ester to the carboxylic acid and an alcohol, or by a base in the process of saponification, in which you will produce a salt of a carboxylic acid and an alcohol. So when you look at this flow chart, okay, you can see that the lipids that contain fatty acids can be broadly categorized into three types. Waxes, which are formed by some kind of a long-chain alcohol and a fatty acid, so that's your garden variety fatty acid. Triacylglycerols, so glycerol, part of the name stands for, well, glycerol, and triacyl stands for 3 molecules of fatty acids. Glycerophospholipids, which contain glycerol, 2 fatty acids, and some other bells and whistles. And sphingolipids, which contain sphingosine, organic amine, fatty acid, and some other bells and whistles. Lipids are super common in biological systems, okay, and the fact that they are not soluble in water is actually very important for their function. So we're going to start with the fatty acids. I'm going to scroll back and just remind you what a fatty acid is, okay? So if you look at this formula right here, you can see that a fatty acid can be basically divided into carboxyl group and a hydrocarbon chain. So far, am I making sense? Hydrocarbons, like this, are very nonpolar molecules. Does that make sense? Which makes fatty acids nonpolar, and insoluble in water. Okay? So, two major categories of fatty acids are saturated and unsaturated. We've already encountered these terms when we were talking about hydrocarbons. Remember that? Alkanes, which are saturated because they only contain single bonds. And alkenes and alkynes, which contain double or triple bonds, respectively, and thus considered unsaturated. So, in our future conversations, we're going to use this analogy that we see on the slide, is that saturated fatty acids tend to stack like Pringles in the tub. Does that make sense? Well, unsaturated fatty acids tend to not stack, and they should remind you more of like Lay's or Doritos, chips that don't have such a fantastic similarity in terms of the shape. Okay, that makes sense? So let's talk about what these fatty acids essentially are. So first of all, they have this long unbranched carbon chains. This is really important. They are not branched. Okay? At the end is the carboxylic acid group, COOH. This group. And the typical length for fatty acids is 12 to 18 carbon atoms. All of fatty acids, practically with no exception, are not soluble in water. And as we mentioned before, they can be divided into saturated, so the ones that do not contain double bonds, and unsaturated, when they have double bonds. Now, to expand on that term, if there is only one double bond, we call such fatty acids monounsaturated. If we have two, or more double bonds, we call them polyunsaturated. We're good so far, everyone? Right. So these are just some examples of saturated amino acids. This is kind of a dad joke. If I will say, like, memorize this table, please don't. Don't memorize this table. I'm not going to ask this. Okay? So the only thing that I want to highlight is that we can characterize an amino acid by the ratio of number of carbons to double bonds. And obviously here there are no double bonds, so the second number is 0. Am I making sense? Okay, sounds good? So, here's some questions. Have you ever seen the coconut oil? How does it look? Is it liquid or is it more towards solid? It's more solid, right? I don't think anyone ever saw nutmeg, oil, I mean, I doubt it. Palm oil, anyone? Yeah? So again? But what consistency-wise, is it like solidish, right? Do you know what palm oil is used for in the food industry? It replaces animal fat. So in some sweets and in some milk-based products, palm oil is often added to replace animal fat because it's cheaper and to add like thickness, consistency to the product. Does that make sense? Okay? And animal fat is stearic acid. Okay? We're going to get back to the stearic acid. You can see that, so all these acids, all these fatty acids exemplify that in saturated fatty acids, there are no double bonds, and that the chain of hydrocarbons is not branched. Okay? You can also see something else. The melting point increases as the length of that hydrocarbon chain goes up. That make sense? Okay. So these are a couple of monounsaturated fatty acids. So palmitoleic acid, not really good example. I'm just going to skip on it. So you have one double bond per 16 carbons. But oleic acid can be found in olives and grapeseed. I'm going to highlight these two. Okay, and its melting point is 14 degrees Celsius. What is the typical room temperature? 25, yeah. So is oleic acid liquid at the room temperature? Yes, it is. That's your grapeseed oil or olive oil. That makes sense? And if you will put it in the fridge, what's going to happen to it? Fridge, not freezer. It's going to become solid, right? Because the fridge temperature is about 4 degrees Celsius, which is lower than 14. So you're going to get solid. Again, you can see that the hydrocarbon chains aren't branched, and there's only one double bond right here. Am I making sense? So this is the double bond, and this is the double bond. Sounds good? Everybody? Okay, makes sense? Cool. And then there are poorly unsaturated fatty acids. Okay? So, two double bonds in linoleic and linolenic. Right? Well, linolenic, they're going to have a mistake. It's a 3 double bonds here. Okay, and in arachidonic acid, there are 4. Okay, we're good? So here's the thing. You use cooking oil, I suppose, right? I just wonder, what kind of oil do you use for day-to-day cooking? If it's not a secret. Is it, corn oil? There you go, linolenic acid. Anybody else? Olive oil, that's a previous one. Canola, that's safflower. We use canola oil, soybean oil, okay? Sunflower oil is really big in Russian cuisine. My point is, when you start looking at poorly unsaturated fatty acids, look where the melting points are. They're really low. Does that make sense? So they stay liquid. So basically, so far, you can see the tendency. Look just at the numbers of the melting points. When you go from saturated to monounsaturated to poor unsaturated, the melting points become lower and lower as you increase the number of double bonds. Does that make sense?
The oil in the last one, which and
Arachidonic acid?
yeah.
Why it is solid? It's a fantastic, this is a fantastic question. So, thank you, that's a great question. When we are talking about a fatty acid and an oil or fat, where it can be found, we have to acknowledge that your soybean oil isn't just linoleic acid. Am I making sense? There are other fatty acids present. Do you understand what I'm saying, folks? So for instance, let's go here. Butter at the room temperature, is butter solid or liquid? Solid. Soft but solid, right? But palmitoleic acid is liquid. Is there a problem? No, because palmitoleic acid constitutes a small percentage of all fatty acids in the butter. Am I making sense? So most fatty acid molecules that are found in the butter are molecules of stearic acid. Do you follow? Depends on the ratio. You're going to have liquid oil or solid fat. Does that make sense? Okay, good. Which brings us to this very important, remember the chips story that we had in the very beginning? So now they become more and more important. So unsaturated fatty acids, the ones that have a double bond, can be cis and trans. We had this conversation, folks, about cis and trans isomers, remember? So the simplest example would be this. If you have 2-butene so these hydrogens and these methyl groups, are they on the same side? Like hydrogens on one side, right? But they're all together on top. Methyl groups are on the bottom. Is that a cis or is it a trans? So this will be the trans isomer. Everybody agrees with me? All good? You'll follow me? Trans because the methyl groups are on the opposite sides of the double bond. Making sense? No? It's a definition. So basically, double bond cannot be rotated. Okay? That makes sense? Like you take two wheels that instead of one axle run through two axles through them. They can't rotate. Does that make sense to you? So, if you put two substituents like methyl groups or, crying out loud, finally. Okay, if you put two substituents like methyl group or chlorines on one side, like here in this image, it's at the bottom. You see? They're below. This is cis. If you put them on the opposite sides, it is trans. This is just a definition. Does that make sense? So now, when you look at these guys here, so oleic acid can be cis and can be trans. So in cis configuration, hydrogens at the double bond are on the same side. Right? Making sense? In the trans configuration, they're on opposite side. But I want you to take a look at the shape of the entire molecule. How would you characterize, like, the biggest difference between cis alleic and trans alleic acid molecules, the shape of the molecules? How would you compare them? Oh, come on. You should be better than that. Not that shy. Like, seriously. This is the shape of cis molecule. This is the shape of trans molecule. Trans alleic acid. What does it look like? What is that? It is a line. It's a linear molecule. Okay? What is this? An angle. It's not a triangle. I didn't put the bottom on it, right? But it's an angle. It's not a line molecule. It's angled. It's kinked. Does that make sense? Clear? And most unsaturated fatty acids have cis double bonds. So now let me ask you this. We have two different types of fatty acids. The cis fatty acids have this shape. The trans fatty acids have that shape. So far so good. The saturated fatty acids are also linear. So I have a very simple question. If you need to package a bunch of linear molecules, can you package them tightly? Yeah. Right? If you have a bunch of angular molecules, is it easier to package them tightly or not? No, because what you may end up with is this versus this versus this versus this. Am I making sense right now? So, saturated and trans unsaturated are tight. When you have molecules stacked pretty tightly, do you think the compound, that its appearance, is it going to be liquid or solid when you pack them very tightly? And when you don't, they're going to be what? Liquid. If you would look at melting points, again, this is your poorly unsaturated, multiple kinks, right? The melting point is really low. This is your monounsaturated. The melting point is still relatively low. And this is your saturated. These guys have really high melting point because they are much tighter packaged. Am I making sense? We're going to come back to it when we're going to talk about trans fats again. But I just want to mention that there are some fatty acids that we can synthesize and some fatty acids that we cannot. Okay? For the most part, we cannot synthesize a bunch of poorly unsaturated fatty acids. Now, poorly unsaturated, multiple double bonds, are they kinked? I'm asking you, are they kinked? Multiple double bonds. Remember, double bonds in naturally occurring fatty acids are in the cis conformation. So I'm going to ask again, please. If you have more than one double bond, is this molecule going to be all bent? One double bond gives you a bend. If you have multiple, and they all are in cis conformation, you're going to have multiple bends. Does that make sense? Good? If they have multiple bends, do you expect those fatty acids to have a low or high melting point? Low, which means at the room temperature they're going to be what? If they have low melting point, at the room temperature, are they going to be solid or liquid? Liquid. So, where do we get most of our...
So does multiple bonds cannot affect the, how can I say, this facet having multiple double bonds?
Yes.
Can it not affect the melting points for those molecules because of those bonds?
It will lower, like, okay, if you have 18 carbons, okay, let me go back. I just want to, I think I found some confusion. So this is your saturated amino acid, stearic acid, at the bottom. See that? This guy? How many carbons does it have? 18. How many double bonds?
0.
Melting point, 69 Celsius. How many carbons? No. Carbons, 18. Double bonds? 1. It's the melting point, which is, last time I checked, less than 69. Right? Same number of carbons. How many double bonds? Not 14, minus 5 at this moment. You add one more, just a typo, 3 double bonds, even lower. So the more double bonds you have, the more weird the shape is, the harder it is to stack them, and the lower the melting point is going to be. Do you follow? But my point here is that we get those essential fatty acids to a large extent from plant oils. When we cook or add it to a salad or something else. It's not the only source, we'll get back to this, but it's not the only source. Okay? So now let's talk about this saturated fatty acids. Because we just discussed, they fit close together. Okay? And because they have these long tails, they can very effectively interact by using dispersion forces between the carbon chains. So saturated fatty acids are solid at room temperature. And these guys come from, for the most part, not exclusively, animal fat. As we discussed, palm oil, coconut oil, solids, but there are always exceptions to the rule. Making sense? Now, as we mentioned before, we already discussed it. When you start looking at unsaturated fatty acids, the carbon chains are kinked, which means that there are fewer interactions. Okay, does that make sense? And the melting point is reduced. Okay? Good? Now, this is sort of a dramatic shift of gears here, but let's chat about this. So what about prostaglandins? Prostaglandins are indeed fatty substances that are produced in the cells, and they are formed in the process of metabolizing the arachidonic acid. Okay? Why prostaglandins are important? Regulate blood pressure, smooth muscle relaxation. To be fair, they even mediate inflammation, they can mediate fever, they can mediate pain. A lot of functions are mediated by prostaglandins. So you see that this arachidonic acid, okay, when it is metabolized, forms prostaglandin F2, which is responsible for pain and fever. And the analgesics, like ibuprofen or Tylenol, they will block the enzymes that convert arachidonic acid into this prostaglandins. Am I making sense? So essentially, again, I think it's kind of important to understand that when we talk about drugs like analgesics or antipyretics, the ones that reduce the fever or relieve the pain, we're not curing the source. Am I making sense? If you sprained your ankle and you take ibuprofen for pain or Tylenol for pain, your ankle is still sprained. It just doesn't hurt as much. Right? If you have flu and you take Tylenol or ibuprofen for fever, your flu doesn't go anywhere. Just your fever is gone. Making sense, everyone? All right. So these are some non-steroidal anti-inflammatory drugs. There are two large categories, as you can imagine. Steroids and these guys, NSAIDs. So, there's, aspirin, which is, aspirin, acetylsalicylic acid, ibuprofen, naproxen. There are other drugs, ketoprofen, which I think now is not widely used in the United States because it has a variety of side effects. They don't include Tylenol here, acetaminophen, but technically it is a non-steroidal anti-inflammatory drug. Okay? But here's my question. You'll probably took those NSAIDs in your life, right? You were told by doctors sometimes, take some ibuprofen or Tylenol, right? Am I correct? When physician tells you to take this NSAIDs, what do they warn you about? Like, what symptoms should you watch for? Let's say you have a sprained ankle, right? You start taking ibuprofen. Physician, what would they tell you to? Like, you should stop if... Well, yeah, but okay, it helps, but what is the side effect of all non-steroidal anti-inflammatory drugs? It's pretty well known. That's antihistamines. Gastritis. Stomach irritation. Now, this is not the example, but this is one of the elegant things. Prostaglandins mediate inflammation, pain, and fever, right? They also, not the same prostaglandins, but very similar molecules, control the mucus production in your stomach, the mucus that protects your stomach from acid. Am I clear? When you take NSAIDs, you block the synthesis of prostaglandins. So you don't have fever, you don't have pain, but the mucosal lining of your stomach suffers. The mucus becomes thin as it reaches the cells, and you have gastritis. It's fully reversible, like you stop doing this and it goes back to normal. Make sense? But it's one of the interesting facts about how prostaglandins regulate a variety of different functions in the body.
So when those patients are like given disease or stomach acids to give those medications.
Say it again?
It's not something good to give those who suffer from.
Oh yeah, so here's the thing. That's a great comment, actually. Yes, if somebody has peptic ulcer, right, or already has gastritis, you should think twice about that, because they will worsen the symptoms. Absolutely, yes. Okay. Now, these ones, the omega-3 fatty acids, I spent a decent amount of time doing cardiovascular research, so I'm less prone to the overall hype about that. So unsaturated fatty acids that are called omega-6. Why do we call them omega-6? Omega is the last letter in the Greek alphabet. So this carbon right here is an omega carbon, the very last one. Then we start counting from that omega, which is number 1. So we go 1, 2, 3, 4, 5, and at the carbon 6 from the very end, we have a double bond. Making sense? Good? So this is why we call them omega-6 fatty acids. If we have a double bond at the carbon number 3, essentially here, that would be omega-3 fatty acid. Okay? So, I have some issues with this statement. Well, they are more beneficial. Yes. So, for instance, a lot of fatty fish, such as salmon, for example, or herring, they contain cold water fish, cod, okay? They contain a lot of omega-3 fatty acids, okay? So you can see examples of these ones, but why do we care? So it's been shown that if you increase the proportion of omega-3 fatty acids in the food of mice, that's important, animals for the most part, okay? You're going to reduce the possibility of blood clots, and you're going to reduce the risk for atherosclerosis. Does that make sense? And it's been known that what's called Mediterranean diet, that is rich in fish and plant oils, so therefore rich in unsaturated fatty acids, it is associated with cardiovascular benefits. Am I making sense? Good? But I just want to tell you, it's also been shown that consumption of saturated fatty acids, such as the ones that are in the butter or pork or milk, is not associated with any significant increase in the risk of the heart disease. Does that make sense? So all this fat-free food is basically a scam. If you want to buy whole milk, buy whole milk. If you want to have some butter on your steak, that's perfect. Make sense? Obviously, I'm not referring to the situation when somebody decides to eat like 10 sticks of butter a day, or half a pig. You know, that's, your liver will do some nasty things with those fats. But an average regular diet, if there's any, which contains a fair amount of saturated fatty acids, does not lead to the increased risk of cardiovascular disease. There's something else there. Okay? Now, waxes.
So they just say that because it increases the
Now let's talk about these esters. So we already mentioned fatty acids. Now we're going to talk about waxes and triacylglycerols. So we're going to talk about where waxes are found, but first of all, what waxes are formed by. So it is an ester. So remember that the ester bond here, okay? So this ester bond is always formed by a carboxylic acid, and fatty acids are carboxylic acids, and an alcohol. In the case of waxes, it's going to be some kind of a long chain alcohol. Sounds good? So let me ask you this. Fatty acids, are they hydrophobic or hydrophilic? Are they polar or non-polar? Do they dissolve in water or not? Fatty acids. They don't dissolve in water, right? Now, do you remember what that story about alcohols? What happens to the ability of alcohols to mix with water as you increase the number of carbons? They don't dissolve in water, right? So you have, hear me out, a really long hydrocarbon chain of a fatty acid, and you have a long hydrocarbon chain with alcohol. Am I making sense? When you have two long hydrocarbon chains that are horribly nonpolar, you're going to get some very, very hydrophobic, water-repelling substance. Am I making sense? So waxes are hydrophobic, which means they repel water, and when they cover the plant leaf, they keep the water inside. Am I making sense? Now, it's not a poetic thing, but I encourage you, if you are up early in the morning and there is a morning dew on the leaves or grass, take a close look how these drops of water look like. Anyone ever noticed? So that would look like this. You have a surface of a leaf, right? And the water basically forms a little sphere. Am I making sense? But if you will apply that same water to, say, a piece of paper, it will be completely absorbed. A piece of paper is hydrophilic. It readily interacts with water. The surface of the leaf is hydrophobic because of waxes.